Okay, this video is for 4.3. So a lot of it we talked about in 4.2, but now we're just going to emphasize the inflection points in this section and also taking all the information that we learn and graphing the function with accuracy. All right, so let's jump over to the PowerPoint. Make this a little bigger. Okay. So the first derivative test we learned in 4.2, and we stated that if the derivative changes from positive to negative, so up then down, we know the critical point in the middle where the change in increase to decrease is a maximum. And if the derivative goes from negative to positive, so down and then up, then we know the critical value between the change in decreasing to increasing is a minimum. We also know that if it doesn't change, it goes down, down, negative, negative, or positive, positive, up, up, then the critical value between those two must be an inflection point, a change in concavity, the point at which a frown turns upside down. Okay. So this is easy to look at here. Max, we have increasing, decreasing, indicates C is a max. Decreasing, increasing, indicating C is a min. Increasing, increasing, indicating C is an inflection point, and same with decreasing. Let's talk concavity, so smiles and frowns. So a function is called concave up if it looks like a smile, and it's called concave down if it looks like a frown. So recall that the second derivative, when the second derivative is positive, we have concave up, and when the second derivative is negative, we are concave down. So if we look at this figure, we can see that here from A to B is concave up, and halfway between our min here and our max here is an inflection point, because at some point we change from smiling into a frown between P and Q. It was also an inflection point because we changed from the frown back to a smile or concave up. Okay, so similarly, the slopes of tangent lines decrease from left to right on the interval from B to C. B to C, saying the tangent lines decrease. Okay, so that's true because you're going to have a steeper tangent line here, and eventually you're going to bottom out here at a tangent line of 0. A point where a curve changes its direction is called direction of concavity is called an inflection point, which we talked about. The P and the Q in that last example were your inflection points. Did I miss anything? No. Okay. So concavity test is just taking it a step farther and verifying that the critical point that we believe is a inflection point, just do a second derivative. So we would find if the second derivative was positive, then we know we indeed have a concave up portion of the original function. And if we have the second derivative being negative, we know we are concave down. Okay, so this is called the second derivative test, or the test for concavity. Let's try this example. So we have a function y equals x to the fourth minus 4x cubed. We not only want to find the inflection points and the max and the mins, but we also want to sketch the graph when we're done. So let's jump to our whiteboard so that we can do some calculations. Okay, so this is the same thing we did in the 4.2 video. We take a look at our function, which our function this time is x to the fourth minus 4x cubed. Step 1 is to take the derivative. So we have, using our power rule, 4x cubed minus 12x squared. After we find the derivative, we are going to set it equal to 0 and solve for x. So here, both my terms have x's in them. technically both of them have x squareds, and they are both divisible by 4. So I'm going to factor out greatest common factors before I do anything else. So I'm going to take a 4x squared out, leaving me with x minus 3. I have just created a product to 0. So I can use my zero product property now to solve for the critical values. Okay, so we have 4x squared as one of the pieces of the product and x minus 3 as the other. So time is equal to 4x squared times x minus 3. We set it equal to 0. We can set each piece of the product equal to 0 separately because we know that in order to multiply and get 0, one of these pieces had to be 0 to start with. So now we divide by 4 because we're undoing PEMDAS when we solve for x. So we get x squared is equal to 0. Square root both sides. Technically, it does need the plus or minus, even though it has no effect on the result because the square root of 0 is just 0. So 0 is one of our critical values. The other one, we add 3 to both sides, and we get x equals 3 is our other one. So we have two critical values, 0 and 3. Let's put this on a number line. So we are looking at the critical value of 0 and the critical value of 3. We need to pick test points in between each individual critical value. So to the left here, I'm going to use -1. In between, I'll use +1. And to the right here, I will use 4. So I need to now test the first derivative. We'll start with the first derivative. We need to put -1 in the first derivative, 1 and 4, in order to test whether we are increasing or decreasing, and whether our critical values are mins or maxes. Okay, so recall our derivative was 4x cubed minus 12x squared. So the derivative at our first critical point, which is 0, is equal to 0 because each one of our terms has an x in it, which makes all terms go to 0. So, oh, shoot. I was going to say the only way that happens is if it's a critical value, but that's because I put the critical value in there instead of the test point. So if I was in class, one of you hopefully would have corrected me and told me that's not a test point. Our test point is -1, so we need to put -1 in for every one of the x's in the derivative. Now we have a -1 cubed. A -1 cubed is going to stay -1 because it's an odd power, so it's still negative. And we have a -1 squared. That's going to turn positive. Okay, so we get a -4 minus 12 is going to be negative. So to the left of the critical value 0, we have a negative derivative, which indicates that the function, the original function, is decreasing to the left of the critical value of 0. So let's put in our next test point, which is +1. Hold on, gotta erase. There we go. So let's put in +1 into the function and calculate. Feeling like this is going to be positive, but let's see. So we have 4 times 1, which is 4, -12 times 1, which is -12. Oh, I'm definitely wrong. This is negative. So between 0 and 3, we are still producing a negative derivative, indicating we are still in a decreasing pattern between 0 and 3. Let's do our last test point, which is +4. That's the test point that's to the right of the critical value of 3. So let's put +4 in here and see what we produce. 4 cubed is a much bigger number. So we have 4 cubed, which gives us 64. still have to multiply that by 4. We have 4 squared, which is 16. Okay, so 4 times 64 gives us 256. 16 times 12 gives us 192. Now 192 is a smaller number than 256, which means the result, doesn't matter what the number is, but the result itself is going to be positive, indicating that to the right of 3, we have a function that is increasing. So let's take a look at what we know so far. Okay, so we have critical values 0 and 3. We tested -1 and found that the derivative is negative. We tested 1, +1, and found, oops, just kidding, that our derivative is still negative. We tested +4 and found that our derivative is positive. So we're looking at a function that has an inflection point, and we can see here that the 3 is a minimum. And our function looks something like this. There is an inflection point at 0, and there is a min at 3. So that's what I know so far, but we do want to use the second derivative test in order to determine concavity, to make sure that we have concave up. It looks like we have 2 concave up sections, so I am expecting the second derivative to show 2 positives when we plug in these values. So let's first find the second derivative. So our original function was x to the 4th minus 4x cubed. Our derivative, first derivative, was 4x cubed minus 12x squared. And our second derivative is doing the power rules again. So we have 12x squared minus 24x. So we're going to use this second derivative to determine concavity. So let's do that. So we have the second derivative is equal to 12x squared minus 24x. I'm leaving the parentheses for us to plug in some numbers. And we want to check concavity at these spots. Now, if I plug in the critical values, I should get 0 at the second derivative because those are inflection points. So I need to put my test points in. So at -1, our first test point, the test point to the left of 0, let's see what's happening with this second derivative. Again, we expect it to be positive because we drew a graph that we expect to be concave up. So we have a +1 because -1 squared is +1, so that's 12. We have a negative times a negative, so that gives you a +24. So our second derivative is positive. So to the left of 0, we are showing concave up. Now let's put in our test point, +1. Just erase the negative signs. So we're going to put our +1 in there. So we have +1 times 12 is 12. +1 times -24 is negative. 24 is a bigger negative than 12, so that means our overall answer will be negative. So we expect between 0 and 3 to be concave down. Oh, I don't know if I expected that. I'll have to take a look at our picture again. Let's do the last test point. So the last test point we have is to the right of our critical value of 3, which we chose 4 as our last test point. Okay, so we have 4 squared, which is 16, minus 24 times 4. So we got to find those values. So 12 times 16 we calculated before. I believe it was 192. Yes. Okay, 192, and we are subtracting because there's only one negative. 24 times 4 is 96. So we are subtracting a smaller number, which means we are going to come out to a positive answer. And to the right of 3, it is again smiling, concave up. Let's draw this picture. axes. This is our y-axis. This is our x-axis. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. A quick thingy. Oh, before we do this, my apologies, we haven't finished yet. So we know some things, right? We know that we have an inflection point at x. Let's write this out actually. So we have an inflection point at x equals 0. We know that we have a min. We found that we have a min at x equals 3. We know that to the left of 0, we are concave up according to the second derivative test. Between 0 and 3, we're concave down, and to the right of 3, we're concave up again. For the first derivative test, we know that we were decreasing, and then increasing. So the things that we need to find are the y values to these critical points, because this is the critical point 0, comma, I have no idea. And this is the point 3, comma, I also don't know. But we can find those by using, guessed it, the original equation. So remember, these are y values to the original function. So we need to plug these into the original function in order to find their y's. So our original function was x to the 4th minus 4x cubed. So let's find the y value for the inflection point x equals 0. So 0 to the 4th minus 4 times 0 cubed gives you 0. So our inflection point is the point 0, 0. So that's important to know. So we are going to need to use the point 0, 0 at the point in which we have inflection. Let's now calculate the y value for the x of 3, our critical value of 3. So we have 3 in for every x, and we get 3 raised to the 4th power. Let's calculate 3 raised to the 4th power. 3 to the 4th. 81. And we have 3 cubed, 27. So we have minus 4 times 27. 27 times 4 is 108. So we have 81 minus 108. 81 minus 108 is negative 27. So we have our minimum critical value is the point 3 comma negative 27. Okay, we needed those y values before we could accurately draw this function. Okay, so let's do this again. We have our y-axis, and we need actually a much bigger negative y-axis because we just found that minimum. So I'm going to bring the x-axis up here. 3, 4, 5. 1, 2, 3. We'll do 3. Hopefully that's enough. 3, 4, 5. And 1, 2, 3, 4, 5. Negative. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Shoot, we're not going to get low enough to negative 27. I'm going to have to redo this. Okay, let's try this again. I'm going to write smaller. I'm just making my tick marks, so bear with me. Okay, so negative 27 is going to be right here at the bottom. I'm just going to have to take my word for it. And all these dark ones are the 5 markers. So I'll clear that up a little bit, because if you have too much numbers going in here, then it gets a little cluttered. So I don't want the clutter. Okay, now let's draw. All right, so first thing we know is that the inflection point is at 0, 0. So let's put a point at 0, 0. We also know that there's a point at 3, 27. So I'm going to go over to the right 3 and down 27 and put my 327 point. We know that that's a minimum. So we have 2 points here. And if we recall from what we learned on the first derivative test, we learned that we are decreasing on the left side of 0. We are still decreasing between 0 and 3, and then we increase. So if we consider, again, these are some imaginary walls here. This imaginary wall is supposed to be here, so let me fix that. The decreases between here. That's better. Okay, and we know that. We also know from the second derivative test that we are concave up here, concave down here, concave up here. So with that being said, we know that we need to come down to this point with a concave up decreasing. We then need to continue to decrease, but it needs to be at a concave down. So I'm going to come here, I'm going to concave down, and then concave up. So the only other things that make this more accurate is I need to find the x-intercept. Okay, if I wanted to find that x-intercept, that would be helpful. I already know the other x-intercept and y-intercept, it's over here, but knowing where this function then crosses the x-axis again, it would make this more accurate. But I'm not asking you to do that, because that's very much an algebra thing. Not that we're not very far from algebra right now. So that is the graph of the original function, y equals x to the 4th minus 4x cubed. This is what it looks like. Okay, so go back to the PowerPoint. Give me one moment. We're doing this from home, so there might be some interruptions. Okay, so our last example we'll do together is looking at the curve x cubed negative x cubed plus 4x minus 8. And we want to do the same thing. We want to find our max and mins and inflection points, and then we want to sketch the curve. So let's do this again. So we're going to go to our whiteboard. Okay, we have y is equal to negative x cubed plus 4x minus 8. Our derivative is y prime is equal to negative 3x squared plus 4. Remember, the derivative of a constant is 0, so the negative 8 goes away. So knowing our derivative, our next step would be to set it equal to 0 and solve for x in order to find all of our critical values. So we have 0 equals negative 3x squared plus 4. Subtract 4 on both sides, so we have negative 4 is equal to negative 3x squared. Divide by negative 3, so we have a negative divided by a negative, so the negatives are going to go away. I'm just going to keep this in fraction form, so I have 4/3 is equal to x squared. We know in order to get rid of a square, we need to square root and consider the plus or minus answers. So we have square root plus or minus the square root of 4/3. So we have a critical value of positive square root. That was messy. We have a critical value positive square root of 4/3, and we have the negative square root of 4/3. Okay, and that's just some value. Now we probably should figure out what that value is because we have to plot this on a number line, and we need to have some approximate idea of where that falls on the number line in order to grab proper test points. So let's square root 4/3. Root, okay. So I'm getting approximately 1.15. Okay, so this is approximately positive 1.15, and this is approximately negative 1.15. So that at least gives us a ballpark of where these are going to fall on the number line so we can choose proper test points. So if we're looking at our number line, we have a negative square root of 4/3, which is approximately negative 1.15, and our other critical value is positive square root of 4/3, which is approximately positive 1.15. So now we have to pick our test points. So the easiest one in the middle is 0. I love using 0 as whenever I can. Now I just need a number smaller than negative 1.15, so I'm going to use -2, and a number bigger, so I'm just going to use +2. So we're going to have test points -2, 0, and 2. Okay. Just writing this down on my little notes so I don't forget what we chose. Okay, so next steps now that we have our test points is to use the test points to determine whether we are increasing or decreasing on the original function using our derivative. So our derivative that we found was negative 3x squared plus 4. Let's put in our first test point. Our first test point was -2. Again, we're not looking for what the value is, we're looking for the sign. So a -2 squared is a +4. A +4 times a -3 is a -12, plus 4 is going to come out to be negative. So I'm going to mark to the left of negative square root of 4/3 is a negative derivative indicating decreasing function. Okay, now let's put our next test point in, which is 0. Okay, so when we put 0 in, we have this term goes to 0 because the whole thing is 0, and plus 4. So we see that we have a positive derivative at the test point of 0, which indicates that the original function is increasing. Last test point, we are going to use +2. Calculate the sign on this one. So we have a +2 squared, which is 4, times -3 is -12, plus 4 comes out to be, again, negative. So to the right of positive square root of 4/3, we have a positive, no, just kidding, sorry, we have a negative derivative indicating that we are back to decreasing on the original function. Let's draw this out on our number line so we can really visualize what we've found. We have a critical value at negative square root of 4/3 and a critical value at positive square root of 4/3. We chose test points -2, 0, and 2. And we have found that the derivative at -2 was negative, so we're decreasing. The derivative at 0 was positive, increasing. And the derivative at +2 was negative, decreasing. So we can see that the negative square root of 4/3 looks like a minimum, and the positive square root of 4/3 looks like a maximum. So that's what we know so far. Let's now put those test points into the second derivative. In order to do that, we need to calculate the second derivative. So let's go back. We have the first derivative we had calculated at -3x squared plus 4. Our second derivative would be -6x. Oh, well, that's going to make our calculations fairly simple to calculate. So we have the second derivative. We are going to find the second derivative at the first test point, -2. that in, -2. So a negative times a negative is going to give us a positive. So to the left of -square root of 4/3, we have a positive second derivative, which indicates we are concave up. Let's put our next test point in, which is 0. And that's going to come out to be 0. Interesting. So one thing I forgot to mention, and I'm just realizing this now with this problem, thank goodness I picked that test point. We didn't solve set this equal to 0. So the first derivative test is guaranteed to find all the mins and maxes and can find inflection points, but I forgot to mention that you may not find all the inflection points with the first derivative test. Some inflection points do not have tangent lines that are 0. They are still inflection points, but they have tangent lines that are something other than 0. They might have vertical lines. So you need to set your second derivative also equal to 0 just to make sure that there aren't any other inflection points. And when we do that, we get x equals 0. So 0 actually is an inflection point, which is why when we plugged our test point of 0 into the second derivative, we got 0. We have an inflection point at 0, so we have to mark that on our grid. Inflection point. So we need to take other test points. So if I'm looking at this, here's 0 is now marked as an inflection point. We have -square root of 4/3, which is approximately -1.15, and a positive square root of 4/3, same number but positive. So we're going to need different test points now. I'm going to need a test point here. Let's go with -1. So a test point here, let's go with +1. So we have -1 and +1. So we need to test those two in this derivative test. Okay, so let's do that. Erasing. There we go. All right, so let's put in second derivative at a number. Okay, let's test -1. So we have a negative times a negative over here, which is going to give us a positive. So we can mark that we are concave up to the left of 0. We're still concave up. Let's take a look at +1. Okay. +1, we have a positive times a negative here, so that's going to give us not a positive, it's going to give us a negative. So we're concave down on the right of 0. Okay. Last test point we have to check is the +2, which is to the right of the positive square root of 4/3. We have +2. The positive times a negative is going to give us a negative, so we are still concave down on the right side of that critical value, which makes sense because those were not inflection points. Our negative and positive square root of 4/3 were mins and maxes we found out. All right, let's go back and recap what we know. So we are looking at a critical value and a critical value of -square root of 4/3 and positive square root of 4/3, again, approximately 1.15. We also found that there is an inflection point that we didn't know about at 0. Using our first derivative test, we found that we are decreasing to the left of this -square root of 4/3. We then increase between the two critical values, and we decrease again. With the second derivative test, we found that we are concave up to the left of 0, and we are concave down to the right of 0. Okay, so it's looking like we have some function that looks like this, where we have a min here and a max here, and an inflection point at 0. Remember, before we can graph this, we do need the y values of each one of these important points. So let's jump back to our original function, y equals negative x cubed plus 4x minus 8. And let's calculate this function at each one of these important points so we have y values to plot so we can be more accurate. So the first important point was negative square root of 4/3. So let's put the negative square root of 4/3 in for every x. This is not going to make our calculations very easy. Square root. Okay. All right, so I'm going to need to grab my graphing calculator to do this one. Type this into my calculator. I don't have a calculator to share on my screen, so I unfortunately can't show you me typing this in, but I am typing a negative. Remember, the negative is the button to the left of enter. Then parentheses, negative square root of 4 divided by 3. Close the parentheses and cube it. Raise it to the third power. Plus 4 times negative, again, square root of 4 divided by 3 minus 8. I press enter. I get a number, and I could put it in fraction form. If you hit math enter enter, it gives you the fraction, but the fraction is hideous. So I'm saying let's do an approximation of negative 11.1, really, but let's go with negative 11. So we have the first point is negative 4/3, approximately negative 1.1. Comma negative 11 is the first critical value with x and y. So let's mark that down so when we graph, we know how to graph that. Well, let's now do the 0. That one should be easier to calculate. Do 0. All this stuff out. There we go. All right, so now let's put 0 in here. Okay, 0 is fairly easy. We have it, this term goes to 0, this term goes to 0, this is just negative 8. So we have the point 0, negative 8. Okay, so we're going to need that when we're graphing. Let's calculate our last one. Our last one is the positive square root of 4/3, approximately positive 1.15. And we could use the 1.15 instead of the annoying square root of 4/3, you'd still get a pretty good reading on the y value, but I'm just gonna stay exact. So to make it easier, I'm going to make the equation live again by scrolling up and hitting enter. And then I'm just going to delete the negative signs out of the 4/3 equation. Or you can just retype it in, it doesn't matter. Okay, so I get a negative 4.9. So I'm going to round this to negative 5, so I get the 4/3 or 1.15 comma negative 5 as my last critical point. All right, we are ready to graph, so let's get graphing. Okay, so if I'm looking at these points, I see y values of negative 5, negative 8, negative 11. So I do need a larger negative y-axis than a positive one. Looking at my points. Okay, and my x's are very small. So 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, 1, 3, 4, 5. 1, 2, 3, 4, 5, and 11. Okay, let's first put the important points. So we have negative 1.15, which is a little bit to the left of negative 1, and goes down to negative 11. So that would be here. We found that that one is a min. And then we have 0, negative 8. So that's negative 5, negative 6, 7, 8. 0, negative 8 is right here. That's an inflection point. And we have 1.15, which is slightly to the right of the first tick mark, and down 5. So that's about here. That one is to be a maximum. So my graph exists completely down here at the bottom of my graph. Not ideal. So please bear with me. I am actually going to redraw this because I didn't have enough room to keep drawing on the bottom. I actually don't need much of the top axis. Oops. Let's draw this again, but this time I'm going to put my axis way up here. One, two, three, four, five. 1, 2, 3, 4, 5. Okay, so now if I plot my points again, negative 1.15, 11, whoops, 11, and 0, negative 8, and 1.15, negative 5. All right, so we have our min, our inflection point, and our max. Now let's discuss what we learned from our derivative test. So our first derivative test, we learned that to the left of, these are our walls, our imaginary walls that I showed you guys how to graph in class when we were still in class. Okay, and I told you guys to use these imaginary walls to help you visualize what this function looks like. So we learned that the first derivative was negative to the left of negative 1.15, so we would be decreasing here. Then we'd be increasing, and then we'd be decreasing again, which taught us that this was a min, this was a max. From our second derivative test, we learned that to the left of the inflection point 0, negative 8, we are fully concave up, and to the right, we're concave down. So we need to follow those rules while we're drawing. So we need to be decreasing and then increasing for this negative point here, and concave up the whole time, turning to concave down. We have ourselves the function that follows all of the rules. Okay, so this concludes 4.3. Let me stop sharing now. Hold on. There we go. There we go. Okay, this concludes 4.3 and how to draw graphs. Remember, I am available to do a virtual office hours through WebEx or Teams or Zoom. We can figure it out. You just have to let me know that you're struggling and I can set it up with you. A lot of you have been emailing me questions and it seems to be working out as well, so please keep those coming. I should be much quicker at responding this week. I'm now settled in my new home. I just sold my house, so I was a little slow to respond last week. That won't be typical. I don't have a permanent housing right now, so it does make it a little more difficult with getting online, but I promise to change my response rate should be within the day and not 2 days, which is what it was last week. All right, thank you. Have a good week, and I'll see you next week for more calculus.